All right, so I developed a demo to help explain the E-mode and B-mode patterns that various experiments have been seeing in C&B measurements, in particular the bicep 2 experiment that I work on. And I developed this for some outreach talks I've been giving, but it's sort of done in the tradition of a Mr. Wizard style thing that in principle you could set up around your house or better yet in a classroom setting. And it involves a tank of water. Right? So as you can see in this video here, the tank of water is transparent. Right? Its light goes through there in a straight line. And this is meant to be an analogy to space in our modern universe. It's mostly empty, and light can just sail across it in a straight line. It's effectively transparent. A better analogy to the early universe would be if I dump some milk into here and stir it up. Right? So the early universe was ionized, it scattered light aggressively, and would have looked cloudy, kind of like this. Right? You can't see through this so easily anymore in this context. You can see just fine up to the front surface, right? But then you can't see much beyond it. It's kind of like a screen. Or to make another analogy, it's like when you look across the bay in San Francisco, you see the fog rolling in, you see the fog bank. It's fine looking up to that, and then you see nothing beyond it. Right? Most of the light you're actually seeing here is coming off of the front surface, and with the surface of last scattering. In practice, the surface of last scattering surrounds us on all sides, and we're in the center of a sphere in our universe. We call this the observable universe. But the light is coming from very far away. It takes 14 billion years for that light to get to us. And it's endured 14 billion years of expansion. It's had its wavelength stretched all the way out into the microwave range by the time we see it. That's why we call this the cosmic microwave background. So if you imagine sound waves rushing through the early universe, kind of echoes of the Big Bang, they would have alternating high and low pressure planes, shown here. And because this is ionized matter, it would have been heated and cooled a little bit. And so if you imagine an electron in this particular position, right, it's going to see intense light coming in from above and below, but dim from left and right, which means that electron is going to get shaken more in one direction than the other. And so when it scatters light towards us, it's going to have what we call polarization. Right? The electric fields from the light are going to be preferentially moving in one direction versus the other. And we can simulate in this tank here by turning on a couple of lasers. So I'm doing this now. This bright line here represents one of the hot planes of the sound wave. If I then take a polarizing grid and put it in front, this is a filter that lets through one polarization but blocks the other. If I put it in here and I rotate it, you can see immediately that it gets bright in the horizontal position and dim in the vertical. Right? And this is showing you two things. First of all, it's polarized, but second, and just as important, it is polarized parallel or perpendicular to the left-right direction of the wave. And it pretty much has to be. That's the only direction that the particles in this tank know about, the left-right direction of that wave. This relationship doesn't change if you look at it through a mirror. I can do this in the video feed. I can mirror it. And you can see it's still the same, dim and vertical and bright and horizontal. And it doesn't matter how many times I mirror this. I can do it again. And it's still, we're back where we started, dim, vertical, and bright, horizontal. So we call this even symmetry when something doesn't change upon mirroring. And if you have many of these waves cast across the sky instead of just one, then they're going to reflect that underlying symmetry. They're going to produce patterns in our maps that we call E-modes. They're going to look like circles and asterisk patterns. These themselves look unchanged when you look at them through a mirror. Now, a gravitational wave is a little bit more complicated. Right? As the gravitational wave, it's from left to right in the cartoon at the bottom. There are opposite axes, perpendicular axes, where it's squeezing and heating, as I'm showing in red, or stretching and cooling, as shown in blue. And we can mimic the light coming in from the squeezed and heated space with the laser tank above. I'm turning on a pair of lights coming in along diagonals now. And this is an important difference because now the electrons are going to be shaken more in one direction than the other. This now got to be along a diagonal axis. And indeed, if I put a polarizing grid in front and rotate it, that's the case. It should be no surprise, in fact, that if I put a grid in front and rotate it back and forth, that it's going to get dim on a diagonal, and then it'll get bright on the other diagonal. And the key point here is that if I look at this through a mirror, which I can do in the video feed, this is going to get dim on the other diagonal direction, right, upon mirroring. And if I were to mirror yet again, it goes back to where we started, of course. I'll do that once more. So now it's dim along the original 45-degree axis. Right, when something goes back and forth between two states like this, we call this odd symmetry. And the point is that the sound waves have no way of producing this, but the gravitational waves can. And if you have many of them zipping across the sky, they're going to produce characteristic patterns that we call B-modes. So these little pinwheel patterns, the one on the left when mirrored becomes the one on the right, and vice versa. Right? So this is the effect that we have been searching for in our maps, not just us, but many competing experiments as well.